Kartik, can you check the live and see if the audio is good? All right. Hi, everybody. We are going to get started right now. So welcome to ML Monday lecture number 2. If you haven't signed in already, please make sure to do so. So today we're going to be talking about Python dependency management. So like I said last lecture, we're going to kind of be starting from the ground up and really talk about how do you implement all of the models that we talked about last semester and how do you really get these things going. And so Python dependency management is really one of the core parts needed for this, right? So some brief introductions. I'm Alvin. I'm the Director of Education or Education Lead at GatorAI. And I have other ML lecturers who help me throughout these lectures. So we have Kartik, Siobhan, and Sriniket. Kartik and Siobhan are here. They can wave to you guys. They'll be helping me out for the rest of this semester. All right. So this lecture series is mainly about covering beginner machine learning concepts to develop a strong foundational knowledge with a focus on deep learning and neural networks. And in this semester particularly, we're focused on the actual application and how do you build these, right? So for contact, you can reach out to us on Discord, email, or Instagram, right? All of our links are on our link tree. And resources, these slides will be posted in a shared Google Drive folder on our link tree. And we also, of course, will be posting these YouTube live streams on our YouTube channel. All right, so let's get started. First of all, what is a dependency? Can someone give me a definition of what they think a dependency is? Any definition will do. Anyone? Someone gotta give me something. It can be any definition, anything you think of. You there, yeah.
It's like a tool that's required for something else to work.
A tool that is required for something else to work. I like that. I like that. Any other definitions? Does anyone disagree or agree? No? All right. Okay. We'll go. So in terms of like software, right, a dependency is anything that is external to your own code that is required to run it properly, right? So oftentimes when we think of dependencies, we maybe think of other software, other packages or libraries that you import or install that is needed, but that's only a specific subset of the actual dependencies when you think of in terms of a software project, right? So first of all, why are dependencies important? Well, because dependencies are required for creating basically anything useful. Your code by itself will never be able to run properly, right? And so you need dependencies to run it. And of course, having dependencies saves you money, time, and effort, right? Because you don't have to create those dependencies yourself. You can use them already from the ground up, right? So let's take a look at different types of dependencies, right? So like we said, some of the dependencies that people commonly think of are like project packages, right? Packages that your code will import to use, right? So in the terms of Python, these are typical Python libraries that are installed with pip or another Python package manager. Is there anyone here who's like unfamiliar with like Python packages, anything like that? Raise your hand. You don't need to be shy. It's okay. We're learning. No? Okay. Everyone here is familiar with pip. That's good. All right. So you have your code, right? And we can see in the graph that it relies on a set of Python packages, right? If you have a Python project, right? And then we have system packages, right? Which are part of system software. So system packages are shared native libraries that are installed system-wide on the operating system here, right? So installed system-wide means that essentially for every single user on the system, whether it be you or another user on the computer, all of these shared native libraries can be used by them, right? And so these include a lot of shared libraries like .so files, .dll files, right? Those are for Linux-like operating systems and Windows-like operating systems. And then you have things which are called system package managers. Those are things like apt, SSH, curl, which let you manage system packages on your operating system, right? Your operating system is also a dependency in itself, right? Because your operating system is used often to compile your code. It has certain libraries that your code may need, right? And platform differences directly affect whether or not your code will actually run properly, right? And the system behavior of your project, right? Hardware is also another dependency, right? Your CPU architecture, things like your GPUs, of course, affect your code because your code is obviously running on the hardware, right? And finally, the environment too. A lot of people don't even think about this, but the environment, external services and resources, if your project is calling to the internet, if it's using a database, if it's using an API, these are dependencies that your project needs to function properly. Without the internet, it cannot connect to the database, cannot call an API, right? So I want this to kind of just be an example that dependencies are a much more broader thing than when we think of usually in software. And dependencies are a ginormous stack of things that your code needs to run, and your code cannot ever run by itself, basically. All right, so dependency management. So now that we know what are dependencies, we have to define what is dependency management, obviously, right? So good dependency management can be defined by a lot of things, but here are 3 things I want you to think about. Good dependency management is explicitly declaring and tracking all of the dependencies that your code relies on together with your code using some type of version control, right? And so version control is just basically a system that tracks your code as it changes over the course of time, right? So that would be something like Git, right? And I say OS level here at least, because right, you can track your hardware and you can track your environment, dependencies, but oftentimes your hardware is not going to change. You're not going to update your hardware often. Maybe if you're working with cloud services, you have access to the actual hardware that you request. But in most of the times, we're going to be talking about, OS level system software dependencies downwards, right? Okay, so now that we've defined that, good dependency management is also having a process to automatically turn your declared dependencies into a working environment. So a working environment is maybe a development environment, a building app, right? Anything like that, such that it can work properly and that the user who's using your code basically doesn't need to go around and try and fix a bunch of bugs, obscure bugs, in order to use your project, right? And C, having the ability to safely update your dependencies, right? Because obviously over the course of time, you may require different dependencies. You may decide to change which version of the dependencies you're using, and being able to safely update your dependencies is a key feature of good dependency management as your project changes, right? So why is dependency management so important? Why is it important to have good dependency management? It's good to have good dependency management because reproducibility and determinism across the 3 stages, right, of software engineering is essential, right? Let's paint a picture, right? Let's say you're building a Python project, right? Okay, so you've built it out, it works well, it does its job well, and you think you want to share this with other users, right? So you host all of your code out on the internet, right? And some other people decide that they want to use it. But you've never defined your dependencies, you never track them, so then when they start to try and use your code, they don't have the dependencies and they can't run your code, right? So then they ask you, hey, can I get all your dependencies, right? So you have to kind of figure out and remember what your dependencies are. And so you kind of miss a few, and there's a lot of dependencies that are hidden. And so you give those dependencies to your end users, but still it doesn't work, right? And not only that, maybe some of them get it to actually run a little bit, but there's obscure bugs because of the dependencies that your project relies on that you can't even replicate on your own machine. So not only can your end users not reproduce the functionality of your project, you can't even reproduce the errors that your end users are creating. Eventually, you manage to brick your entire project. It doesn't work anymore because you've changed your dependencies so much trying to fix all of this stuff that your project on your own machine doesn't even work anymore. So this is kind of like an idea of what kind of happens to people who are building out Python projects. And Python especially is deemed as kind of dependency hell. Python dependency management is seen as this convoluted mess, right? But it doesn't need to be necessarily, right? And so the reason we have this dependency management skills is so that we can have these reproducibility and this determinism in our code, right? Which is one of the main reasons why we write code, right? Is because we have an input and we can determine its output and it's useful in that way. the moment it becomes indeterministic, right, and produces random outputs, our program or our project is not really that useful anymore. All right, so how do we manage dependencies now that we know we need to manage dependencies properly? So it is achieved through two things, right? Version control, which we've stated before, and something called environment isolation. And once again, I stress that when we're talking about environment isolation, we're talking from the OS layer down, because you can technically isolate your hardware, all of the environments as well, but it's very difficult to do so, and sometimes it's even impossible, right? So version control, like we said before, is a system that tracks and records changes to your code, to your project over time, right? We talked about how you're using Git for that, right? And this also tracks your dependencies over time. So that way, as you're updating your dependencies, Git can track all the dependencies that you're using and make sure that at every step of the project, it knows exactly what dependencies your code needs, right? Environment isolation. Environment isolation is the separation of dependencies across different projects to ensure stability, right? And in most cases, environment isolation is usually separated into virtual machines and virtual environments. And these are two of the biggest types of environment isolation. There's a lot more though, right? So we can see here on the right-hand side, virtual machines and virtual environments and how they isolate the dependencies. So virtual machines, have any of you guys taken operating systems here? Raise your hands. Yes? Yes? No one else? All right, that's fine. So they probably talk about virtual machines a lot in operating systems, right? But essentially the crude definition of a virtual machine is it's the emulation of a physical computer on a computer, right? And that emulation basically operates as its own isolated computer system with its own operating system, its own software, and also usually its own hardware allocation, right? So usually what happens is there's something called a hypervisor that acts on the main computer, right? And it physically splits your hardware resources into different chunks and provides it with a new operating system and its own software. So we can see here, right? There's the hardware, it's all separated. The operating system is separated. The system software is separated. The packages are the Python packages and your code, right? It's all separated, right? But this amount of isolation makes it very difficult to essentially develop your code and test it because you have to kind of separate it all and build it out. So virtual environments are kind of the opposite end of the spectrum from virtual machines. The only thing they isolate in terms of dependencies, because remember, these environment isolations are isolating dependencies. They only isolate A, your code, and B, the packages, right? The Python packages that you're installing or importing with pip or another Python package management system, right? And so basically, it's a self-contained directory that contains a specific Python interpreter along with its own set of installed Python packages, right, in the context of Python. And note that virtual environments are usually sufficient for Python dependency management, depending on the type of virtual environments that you use, right? And we'll talk a little bit about the different types of virtual environments that people use. All right, so, environment management, all right. So an isolated environment, right, tracks dependencies using definition files and lock files. And this is just in general, not just for Python environments, right? So a definition file is essentially a file which declares which dependencies a project needs and their allowed versions. Definition files are created by you, the developer, and they do not track what are called transitive dependencies. So you can see here on the picture on the bottom right, what is a transitive dependency. Let's say that your project is project C, right? Your C is your project, and you're importing directly dependency B, right? But the dependency B requires dependency A to run, right? So as a result, your project, which is C, requires A to run because it needs dependency B, right? So we say that A is transitive dependent of C. A is a transitive dependency of C, right? And so definition files don't track this because they're only tracking direct dependencies that your project requires. Things that you specifically say, I'm installing this, right? And maybe that package on the back end installs other packages that it needs, right? A lock file is different. A lock file records every single exact dependency. And remember, we're talking dependencies from the OS layer down, right here. It records the exact dependency versions used to create a reproducible environment, right? It's usually automatically generated by tooling, as opposed to you basically just writing down which kind of libraries you installed yourself. And log files also track transitive dependencies, right? And we can see that that's really needed here to make sure that your environment is reproducible, right? So we can see here on the picture of the top right kind of how definition files are defined. So we have the different kind of libraries specifically, right? So for example, maybe your virtual environment on the left hand here has scikit-learn, pandas, and numpy, but scikit-learn, pandas, and numpy have a bunch of other dependencies that they will pull in as well. So your definition file only has scikit-learn, numpy, and pandas, but you actually have a ton of transitive dependencies that are not within your definition file, right? So you can see these definition files are not holistic in the dependencies that are required for your project. All right, so specifically for Python dependency management, people say it is so-called a dumpster fire, right? It's dependency hell. And so what makes dependency management for Python specifically painful? There's a lot of reasons, and we'll go through them one by one. So first of all is that standard Python dependency management does not really promote best practice. It does not promote isolating your environments. It does not promote keeping track of your dependencies through definition and lock files, right? And so it's not really the best unless you get really into dependency management. But most of the times, dependency management is seen as sort of for more skilled users of Python, and beginners kind of gloss over it. But at that point, when you've already gone through your Python career, you've not been used to Python dependency management, so you're a bit kind of waddling through it. Two is that most projects require non-Python libraries, right? And system software dependencies such as C++ libraries, which in most cases require third-party tools to manage, right? So say, for example, you have your Python project, you're writing entirely in Python, right? But let's say you want to import NumPy. NumPy is not actually running all of the linear algebra, right? Let's say you're using NumPy for linear algebra calculations. NumPy is not actually running the linear algebra equations on Python because Python is too slow. So what NumPy does is it uses compiled C++ code to essentially run the calculations for it, and NumPy is kind of a wrapper on top of it. And then NumPy feeds you the results of your linear algebra, right? So a lot of the Python libraries that we actually use require non-Python code, right? And that requires a lot of extra tooling because, as you can imagine, C++ is required to be compiled, right? So you have to have a compiler for C++, you have to define what kind of compiler, and it just kind of spirals into a mess from there because Python, in most cases, is requiring libraries that require non-Python code. Also, there are many third-party tools for managing dependencies, and this makes it even more difficult when you're starting out because they're not a standard. Like say, for example, in JavaScript, there's a standard which is NPM, Node Package Manager, that is basically built into it, right? And it lets you do all of the dependency management from the get-go, right? And it's much better prepared than the standards of Python, right? And so there are a lot of third-party tools that you have to kind of research into and weigh the benefits of, and it kind of you get really into the weeds, right, with your dependency management for a Python project. The fourth is the Python interpreter itself is a non-Python package. So Python is a non-Python package dependency. Python, as we can see, is actually system software, right? And system software is software that is installed on your system and it's available for all users on the system, right? And so because it's a system software, Python cannot actually manage itself because the Python installation can only manage Python packages. So Python cannot manage itself, and so if you need different Python versions, you can't manage that using just Python. You have to have something else, and that's kind of why third-party tools have to be used to manage Python, right? So it's system software, and it leads kind of like bloat, and you also have no dependency management over the Python versions you're using. So now we're going to briefly talk about different Python dependency management tools. So there's a lot of Python dependency management tools, right, that I said. And we're going to briefly go over some of the most popular and some of the most used. And then we'll talk a little bit about, when people say what is the best Python dependency management tool, which one should I use? We'll talk about that at the end, right? So the ones we're going to go over today are pip, venv, conda, and uv, right? And like I said, there's a lot of different dependency management tools, and they all manage varying levels of dependency, right? Some manage only your system software, your Python level packages. Some manage some types of system software. Some manage even like more types of system software. It kind of gets into the weeds, right? Each has their own sets of advantages and disadvantages when compared to each other. And especially for us as students, when we're kind of learning and going through this, the thing I would recommend the most is try different ones and learn what you like to use for your Python projects. And also use the ones that are the most common, because if you're ever going to work on a project where other people are working on, it's most likely that you're using a very popular dependency management software or tool, and that you'll probably have to learn how to adopt their strategies, right? So we can here see a graph that people have made before of the different dependency management tools, and so we're going to just be covering a few of them. So we're going to talk about pip. Does anyone not know what pip is or is unfamiliar with pip? That is, raise your hand. Oh, we got someone in the back. Okay. So pip stands for pip installs pip. It's a recursive acronym, so it just goes on and on, right? It is the default package manager that comes with every single Python installation since, I believe, Python 3.4. And essentially what it does is it allows you to install Python packages from the Python package index, or PyPy repository, right? And you can see here we have a link to it. So you can go in there and you can actually see all of the packages that are allowed. And so remember, these Python packages are packages here in this blue circle, right? It's not system software just yet. And so beforehand, pip was actually not able to produce any sort of compiled system software, right? And so eventually there was the introduction of wheels. And wheels allows pip and PyPy to host system software that is needed by Python libraries in a compiled format, right? And so that was a really, really big change, because beforehand, let's say you downloaded a Python package, right? It requires compiled C++ libraries, right? But the compiled C++ libraries can't be hosted on PyPy, right? So you would need to compile the C++ code yourself so that your dependency could use the C++. And if you have, let's say, a different version of the compiler than the compilers that they were using, then all of a sudden your C++ code is not working, your dependency is not working, and your project's not working, right? So wheels include that system software, right? Or those other native libraries already pre-compiled for you to use, which was a huge, huge step in the right direction for pip and Python, right? So their wheels are binary distributions compiled beforehand, and they allow Python packages with non-Python code. And this is a big distinction. Python packages can contain code that are not Python, right? It can contain C++ code. It just has to be distributed in a wheel format, right? And so it allows non-Python code to be in Python packages, right? Without compiling on the user's machine, because it's already compiled beforehand. So this was one of the biggest things, right? Wheels allow for some sorts of system software to be basically embedded inside the Python package, right? And this was one of the biggest things. And we can see here that, even though we have these divisions of dependencies, they kind of blur back and forth, right? And so in some sense, wheels are isolated from other wheels. So say, for example, you install SciPy, right, which is a very popular Python package, and you also install NumPy, which is another popular Python package. So you will get wheels, or a wheel of SciPy, and you will get a wheel of NumPy, right? And so these, both SciPy and NumPy, require optimized C++ libraries in order to run linear algebra equations, right? But they require different versions of the same linear algebra library, right, which is BLAS. They can require different dependencies, the same dependency, but different versions, and they will still work in the same virtual environment because the wheels are isolated, right? Because the wheels are already pre-compiled when they come to you, you can kind of afford that isolation here. And so this is one of the biggest things of wheels. So we can see here in the bottom right again, we have question.
So in a lock file, would it keep track of both of those BLAS dependencies separately?
Yes, exactly. So it would keep track of both of those dependencies. Actually, it's a good question. I believe it would keep track of transitive dependencies, but maybe not. It wouldn't keep track of BLAS because BLAS is the like compiled already within the wheel. So it wouldn't keep track of that because the NumPy wheel already contains everything. So when you download NumPy, it already has the wheel, and that wheel already has everything.
So it would keep track of the NumPy version, but not of the compiled.
Exactly, right? But NumPy might require as dependency other Python libraries that are hosted on PyPy, and those will be transitive dependencies that will need to be declared in your log file, right? Yeah, but the definition file will just include just the things that you decided to install. Like when you said pip install NumPy, NumPy will be the only thing in your definition file. There'll be a bunch of other transitive dependencies that will be in your log file if you have your tool allows you to manage log files. All right, so wheels in some sense are isolated from other wheels, and this is sometimes a good thing, sometimes a bad thing, depends on the requirements of your project. All right, so pip, what are the pros and cons? Well, first of all, pip is easy to use. You just do pip install whatever you want, right, and it installs it. The bad thing is that, another good thing is that it is standard and installed with any Python installation, right, since 3.4. So if you download Python, you have access to pip, you have access to PyPy, you can do whatever you want with any of the Python packages. Cons, so it is a Python package itself, right? So pip can manage pip, but it cannot manage Python, right? Which is bad because you want to manage the different versions of Python. You need to install the Python interpreter to use it, right? Obviously, it cannot manage Python itself. Pip cannot install system software directly, right? It can install system software through the use of wheels, right? When the wheels already contain the pre-compiled, native libraries, but it cannot install different types of system software directly. And also, wheels have to be, hosted somewhere for you to download them, so it has to be classified as a Python package. Also, pip has no automatic log file generation, and it does have some sort of definition files through requirements.txt, but they do not always produce a working environment because of the flexibility of definition files, right? Because let's say somebody's creating a library and they have their own definition file, right? So your definition file is just an amalgamation of other definition files from other developers, right? So let's say you have some dependencies that are not really working properly together. Your definition file might fail because their definition files did not cover all of the cases where the dependencies, conflict with each other. So, that's why it's really important to have a lock file system, right, in your dependency management tooling, and pip obviously does not have this. So next we're going to move on to the next step, right? So, let me go back and also say something. So pip, right, like I said, is a part of Python, the Python installer. And remember that Python is a system software, right? So when you install dependencies for Python using just pip, if you're installing it on no virtual environment, no anything, all of those dependencies are now system software as well, basically. They basically become ingrained with Python. And so let's say you have Python 3.11 or something, 3.11 or something, and you have those dependencies. You can't really have another environment, right, on your system because you already have that one Python system on your computer, right? And so all the dependencies are kind of amalgamated into that. And this is one of the issues with Python dependency management is when you start with one Python version that you will download, right, off of the Python website. And that is the one Python version you have. And then as you work across different projects in your different classes, in your extracurriculars, you have basically sort of a combined environment of all the different projects. And so basically, as you go throughout, you might realize that some of your previous projects are failing, right, because you've been changing your dependencies over time, right? And so this is also one of the cons of pip, right, is that it's installed system-wide if you have a system-wide Python installation, right? Vend, so Vend is the next step up. Pip, there is no environment isolation. It's installed on your computer across the system, right? Vend is like we described before. it only isolates A, your code, and B, Python packages, right? Venv is the default virtual environment management system that comes with Python, right? And it isolates, like I said, Python packages only. And I want you to remember still that even though they're considered Python packages, and we've clearly labeled them as separate in the picture, that Python packages can include some forms of system software because of Wheels, right? Wheels allows for some form of system software to be precompiled and included in Python packages, right? So virtual environments essentially allows you to manage just the Python wheels, right, and Python packages. And normally what happens is you activate a virtual environment using a shell command, so your Python can figure out what Python packages to use. So we have a picture on the bottom right. You have one version of Python, still one version of Python. You still can't manage multiple versions of Python. And you have multiple virtual environments, and your virtual environments can manage different dependencies, right? So you can see here that you have a library called Ansible, right? And you can pip install different versions of it across your different virtual environments, but you're still using the exact same Python version, right? So let's go over some pros and cons. You manage virtual environments. It's better than nothing, right? It's better than just installing everything system-wide and hoping that your different projects don't ever fail on each other. It's standard, right, and installed with any Python installation since 3.3, which is really good, right? So it allows beginners some semblance of how to get it started with dependency management in Python. Cons, right? It's a Python package, so once again, it cannot manage the Python version. All virtual environments must use the same Python version, right? There's still no installation of system software directly that you may need. You still have to install it kind of indirectly through Wheels, such like that. And there's also no automatic lock file or definition file support. There's kind of manual ones where you can do like pip freeze to requirements.txt, but it's not really automatic. And if you were to automate it, you'd have to start doing like shell scripting and stuff like that, which is not really ideal for a Python project, or a big complex one at least. All right, so UV. So UV is the next step up, right? So like we said, Ven could not manage Python itself, but UV can manage Python. And this is kind of what sets it apart. UV is a relatively new Python package dependency management tool. And so a lot of people kind of throw a lot of hype at it. And so I wanted to include it even though I have personally never used it, because a lot of people say it's kind of the end-all be-all of Python dependency package management, right? So by its own terms, it's an extremely fast Python package and project manager written in Rust. It's built with the intention of replacing every other dependency management tool out there. So it's trying to think of replacing pip, venv, conda, which we'll talk about later, and every other one, right? Which is a pretty big goal in my opinion. And UV, like I said, can manage different Python versions. And it also has explicit support for automatic definition and lock file generation for your dependencies, right? Which is a really big thing because the other ones didn't really have that much support for it. Right. So some pros to UV is that it's extremely fast compared to other tools. It can handle Python. I have to change that. It can handle non-Python packages as long as they're defined, and it manages lock files and definition files, right? Some cons to UV, right, is that it's heavier tooling, right? It's a third-party library not included with the Python installation, and that means there's more dependencies to UV, right? And more dependencies means essentially more parts that there can break in your project. It's only able to deal with packages that can be installed with pip, and there's also no support for multi-version environment maintaining. And so those are basically multi-version environments are environments with multiple versions of the same package within one environment. And so that's a more complex project you would have, but some people want that. And so UV doesn't have this. All right, next. So Conda. So Conda is one of the biggest Python dependency management tools out there, if not the biggest, besides pip and venv. So it is a completely different dependency management system, but most people use it for Python projects, right? And so Conda essentially has split the Python ecosystem between all of the Python dependency management tools we've talked about before to just Conda, right? That's how big Conda is. So Conda does not use pip or PyPy for hosting its packages, and it forces packages to be distributed as compiled binaries, similar to Wheels. The biggest difference between Conda and every other package dependency management tool before is that Conda can install almost any type of software and library at the user and system software level, right? Which is a really, really big thing because as you know before, the other tools cannot install that. They would have to install it kind of through Wheels, and sometimes the Wheels obviously wouldn't contain all the system software requirements, right? So Conda makes less assumptions essentially about what system software you have, and it allows you to freely install system software that you need, right? And that's kind of one of the biggest things about Conda that makes it so good. So you might be wondering then, why do Wheels not make Conda obsolete, right? Because Wheels contain system software, Conda allows you to install system software too, but what's the difference? Like I said before, almost anything can be considered a Conda package, so it doesn't need to be hosted as a Python package, it can install literally anything. Conda can even install NPM. You can install another project package manager and run it properly, right? Which is kind of crazy, right? You can use Conda to run NPM, to run Node.js, whatever you want. In that sense, Conda is more like a system package manager, like apt, right, or curl. It can download almost anything. As well, one of the biggest things is that resources are shared amongst the packages in the environment. So, for example, we talked about how before Wheels have isolated dependencies, right? Conda does not assume that, and it essentially allows you to install closer to the hardware level dependencies that are too large or too complex to be bundled separately, right? For example, there are a lot of GPU drivers, right, that are like absolutely ginormous. They're like multiple gigabytes large, right? And so if every single Python package that required those GPU drivers were to isolate them in their own Wheels, well then next thing you know, you have a project that's maybe hundreds of gigabytes large, right? And Conda doesn't do this. Conda makes sure that everything is shared across your single environment, right? Which is also a good thing. So we can see a table here of what Conda can do, right, versus Python. And we want to think about the virtual environments, right? So pip and venv are virtual environments, and Conda's more similar to a virtual environment at the system software level, right? And it still uses system software to some degree, but it allows you to have more control of your system software than something like Wheels from pip. All right, so pros and cons of Conda, right? It's a multi-platform support, many different types of packages. They're all distributed as binaries, so the user has no issue using them, right? If there is a binary for their operating system and their hardware. It assumes, right, very little about system software dependencies, and you can install a lot of system software dependencies to make sure your project runs properly. You can also use pip inside Conda environments, which is why sometimes people still like to use it, because even if you're using pip, you can combine it with Conda, and you can combine the dependencies you need from PyPy and also the Anaconda package repository. Cons is that Conda is very, very heavy tooling, unless you're considering like other alternatives to installing Conda, but even then it's still quite heavy compared to just say the Python, regular Python installation with pip, right? And it also still has no automatic lock file support, which is not the best, right? But there is manual version, so UV wins in that part where it has the automatic definition and lock file support, right? So we're actually going to have a brief demo now. And yeah, you want to sign in, you can sign in, but we're going to have a brief demo now of actually running 3 of the different tools and seeing exactly how they work. So I'm going to have this here. I'm going to have this here. So this is a Jupyter notebook, and we're just going to use it essentially to guide us through our process. So first of all, we're going to start with using pip, right? So pip is the standard Python package, right? Dependency management tool that we talked about. And so once you have Python installed from the Python website, you can follow along. And if you guys want to follow along on your laptops, I highly recommend you to. So I'm on Windows, so I have to change the commands I'm using a little bit. But if you're on Mac OS or Linux, you can copy these word by word and run them. So we're gonna run Python. So we have Python, right? And we can see that we're in the shell. So we can just do import sys and platform. And I'm just gonna do the first one, but we can import Python, or not import. We can basically display the version of Python that we're using, which was already displayed before, but we can see. And we can also print the executable that we're using. So we'll print the executable, and we can see where exactly the executable lives. Oh my god. Sys.executable. And we can see that our Python executable lives right on our system here, and it's installed specifically in local programs, whatever, blah, 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 right? So this is a system-wide installation of Python, right? And so we can, first of all, let's upgrade pip, right? So we're going to exit our Python, right? And we're going to do py-m pip install upgrade pip, right? So we can update the pip version, right, that was installed, and we can see it's collecting, right? And you can see here that it's looking in PyPy, right, which is the Python package index. And so we can see it successfully updates pip, right? Now, let's see if we can install something else, right? Something like NumPy. Oh my god, I forget that I'm not in Ubuntu right now. So we can run pip install NumPy, and we can see I already have NumPy installed, but if you would run it, you would get NumPy, right? Now let's see where NumPy exists, right? Because we're using pip, we expect it to live on the system, right? Not in a virtual environment. So let's see if we can get that, right? Py again. So we'll import NumPy, and then we're going to print exactly where NumPy's file is. And we can see here that is installed, right, in the Python system-wide installation, right? It's not installed in some virtual environment somewhere, right? And so we can see that here. So you can kind of use pip to install, but it's going to be across system-wide if you're just running it straight from your command line. So now I'm going to switch over to Ubuntu because I'm using virtual environments. So now let's use virtual environments. And right, we said virtual environments are the standard for Python packages only. So let's first of all make our virtual environment using this, and we can, it's Python 3 -m venv demo venv. Okay, because equipped ensure pip is not available. I have to activate something. Right. Give me a moment. Oh. Okay. -m venv Python 3 -m venv demo venv. Hopefully this works. All right, so we're creating our demo, our environment folder, right? So this is our virtual environment. And we can see that all the Python packages should theoretically live in this directory, right? So we're going to activate our virtual environment using the thing. So we're going to do /activate. And now we've activated our demo virtual environment, right? And we can see here on the left-hand side, demo venv, which shows that you're inside the virtual environment that you created with venv, right? So now what we can do is we can run a command again to install Python. I mean, not install Python, install NumPy, right? So we can do python-3m pip install NumPy, right? So it's going to look again once, and it's going to download NumPy for us, right? So we can see here that we successfully installed NumPy. And now let's see where NumPy lives, right? Theoretically, because we ran this command in a virtual environment, it should be stored in this directory, right? So let's do Python 3. And we're going to, once again, import NumPy, right? Oh my gosh. What is going on here? Must define. And 2. Interesting. Well, this is always such a great You just have to take my word for it. It will live in the virtual environment. I'm having some troubles because I have my own virtual environment system. I use Conda on Ubuntu. So let's now work with Conda environments, right? So I'm going to spawn a new Ubuntu, right? And so we're essentially using Conda now environments. So you can download Conda using any kind of installer that you want. I recommend Mini Conda because it is the Conda installer that requires the least amount of other dependencies along with Conda, right? So once you install Conda, and I already have Conda installed, you can activate Conda, right? And you can create a Conda virtual environment, right? So we'll do conda create /n test, and you can see here that we can specify our Python version, right? That's great, right? Because none of the other tools could do that. So now we can specify Python 3.11, right? We'll see that there is a bunch of other libraries that it wants us to include as well. Some of these are system software libraries that you can see that are required. And so it's going to install all these system software libraries for us, right? And that's something that kind of the other things would expect you to have, right? So now we can see to activate this environment, use conda activate test, right? So let's activate test, right? And let's see what our Python version is because it should be the exact same, right? And you can see we have Python version 3.11, right? That's great. Now we're going to install a non-Python package. Like I said, you can install npm, so that's what we're going to do. We're going to install npm. So we're going to do conda install Node.js, and we can see that it works. We can install Node.js, which is a JavaScript library, inside Conda, which is normally meant for Python packages or Python projects, right? So there, we have it. So now let's see if we can actually get it to work, right? So we see we have Node. We have access to Node in our virtual environment, right? Which is crazy. And do npm -- version, right? Because npm install with Node.js, and we can even see where exactly it lives, right? So you can see that it lives exactly in the test bin, right, for our environment, right, because we're in the test environment. So that's really cool, and you can shows how powerful Conda is, but it's just very, very big and heavy. I think that'll be the end of our lecture today. If you guys have any questions, please feel free to ask me. Either just raise your hand or you can come up to me after class. But I hope you guys found this informative and useful, and that you employ these dependency management techniques in your own projects to make sure that you guys don't break everything. But yeah, that's about it for me. So thank you very much. Have a good day.